periodic table. In 1913, Henry Moseley showed that the atomic number of an element is a more fundamental property than its atomic mass. So, Mendeleev's periodic law was modified and atomic number was adopted as the basis of the modern periodic table. The modern periodic law is stated as: properties of elements are a periodic function of their atomic number. Atomic number is the number of protons in an atom, and it increases by 1 unit in going from one element to the next. Elements, when arranged in order of increasing atomic number, lead us to the classification known as the modern periodic table. The properties of elements could be predicted with more precision when elements were arranged on the basis of increasing atomic number. For example, the sodium atom contains 11 protons and 11 electrons. Therefore, the atomic number of sodium is 11. Similarly, the atomic number of magnesium is 12. Since the atomic number of magnesium is higher than that of sodium, magnesium is placed after sodium in the modern periodic table. Let's examine the features of the table. Elements are arranged in an increasing order of their atomic numbers. Horizontal rows in the periodic table are called periods, and vertical columns in the table are called groups. Elements in the modern periodic table are arranged in 7 periods and 18 groups. You can locate an element in the periodic table by referring to the relevant period and group. For example, the elements present in group 1 of the periodic table are lithium, sodium, potassium, rubidium, cesium, and francium. The electronic configuration of lithium is 2, 1. Sodium is 2, 8, 1. And potassium is 2, 8, 8, 1. All these elements contain the same number of valence electrons. Valence electrons are the electrons present in the outermost shell. Hence, we can conclude that the elements present in a group will have the same number of valence electrons. Let us take the example of fluorine and chlorine, which belong to group 17 in the periodic table. The electronic configuration of fluorine is 2, 7, and chlorine is 2, 8, 7. Both of them have the same number of valence electrons. Hence, we can say that the groups in the periodic table signify an identical outer shell electronic configuration. The number of shells also increases as we go down the group. There is an anomaly when it comes to the position of hydrogen in the periodic table, as it can be placed either in group 1 or group 17 of the first period. Like alkali metals, hydrogen combines with oxygen, sulfur, and halogens to form similar compounds. On the other hand, like halogens, hydrogen exists as a diatomic molecule and combines with metals and non-metals to form covalent compounds. When we look at the long form of periodic table, we find that the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon are present in the second period. The electronic configuration of lithium is 2,1. Beryllium is 2,2. Boron is 2,3. Carbon is 2,4. And so on. We can see that these elements do not have the same number of valence electrons, but they have the same number of shells. The number of valence electrons increases by 1 unit. As the atomic number increases by 1 unit on moving from left to right in a period. The position of elements in groups depends on the number of valence electrons in an atom. The atoms of different elements with the same number of occupied shells belong to the same period. For example, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon belong to the third period of the modern periodic table, since the electrons in these atoms of elements are filled in the K, L, M, the electronic configuration of sodium is 2, 8, 1, and magnesium is 2, 8, 2. In each period, a new electronic shell gets filled. Let us see how many elements are present in different periods. For example, first, second, third, and fourth periods. This can be explained on the basis of how many electrons are filled in various shells. We know that the maximum number of electrons that can be accommodated in a shell is given by 2n raised to the power of 2, where n is the number of the given shell from the nucleus. For example, K shell is equal to 2 multiplied by 1 raised to the power of 2 is equal to 2. Hence the first period has 2 elements, that is, hydrogen and helium. L shell is equal to 2 multiplied by 2 raised to the power of 2 is equal to 8. Hence the second period has 8 elements, that is, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. M shell is equal to 2 multiplied by 3 raised to the power of 2, which is equal to 18. But the outermost shell can have only 8 electrons. So the third period has only 8 elements, that is, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. If you begin with group 1, the position of an element in the periodic table tells us about the chemical reactivity. The elements present in the same group will have similar properties as they have the same number of valence electrons. Valence electrons determine the kind and number of bonds formed by the element. In this module, you have learnt that the modern periodic law is stated as properties of elements are a periodic function of their atomic number. Elements are arranged in an increasing order of their atomic numbers. Valence electrons are the electrons present in the outermost shell. The elements present in a group will have the same number of valence electrons. Groups in the periodic table signify an identical outer shell electronic configuration. The position of elements in groups depends on the number of valence electrons in an atom.